This video is about how to estimate speed up when you have multiple processes or multiple threads. Now, the reason why we need to learn this is so we can understand what happens when there are more threads working on a specific task. Right? Now, from grade school, there was a problem where the setup would be if it takes, let's say, 1 day for one painter to paint a house, how many days will it take 2 painters? Now, if it takes 1 day, one painter, I would assume that if there are 2 painters, they would take half a day, right? And similarly, if we said, oh, there are now 4 painters working on the house, we would say, okay, it will take a quarter of a day, right? So the whole idea is the more processes or the more things that we have to work on something, the less time it will take to work on it, right? But in real life, there are some things that have to be done in parallel and some things that can be done only sequentially, right? For example, if you were to say someone is making a dress of some form or some sort of shirt or some article of clothing, there may be some things that people could work on separately, such as, oh, let's cut up the pieces of cloth. That could be done maybe separately. But putting them together, stitching them, it may be that the way sewing machines are designed, only one person could work on it, right? So maybe stitching could be done by only one person, while things like cutting could be done by multiple people. So these are just examples. I'm sure you can come up with a lot of things that are this way in real life, where only one person can work on something at a time, but there are some things where multiple people can work on. All right, so let's use the quiz question, right, that I had. So in a quiz question I gave to you today, I said there's a company that wants to render a 10-minute video. Now, of these 10 minutes, 6 of the 10 are 3D rendered. Right. And if they are to use just one processor to do the rendering, right, it will take 2 hours for one processor to render 6 minutes. And the question was, compare how the work would look like if you had just one processor The second case is 5 processors, and finally 10 processors. Right. So let's do the first one. Right. So for one processor, if rendering for just that 6-minute part, so in the first case, I have 10 minutes of video, and there's 6 minutes of 3D rendering that has to be done, and the rest is just regular 4 minutes. Right. So if these 6 minutes are going to take me 2 hours, then if one processor does the work, it spends 2 hours doing this 6 minutes, right, and spends 4 minutes on the remaining part. So that means it will take 2 hours and 4 minutes to do this work. That's if you have one processor. What if you had 5 processors? 6 minutes of 3D and 4 minutes of regular. Alright, so if I had 5 processes, now remember, if it will take 2 hours for one, then how much time will it take for 5 processes to work on it? Right. And remember, it's just like last time, so 2 hours divided by 5, or in this case, sorry, it's 120 minutes, not 160 minutes. 120 minutes divided by 5. Right. Right. So 24 minutes. So that means if instead of just one person working on this, this could be broken up into 5 pieces, all working at the same time. And at the end of the day, you have 24 minutes. Sorry. So break this into. Sorry, I've not done very well. 1, 2, 3, 4, 5. So if you split it to 5 pieces, and they all worked in parallel, so that means the first part is being done same time as the second part, as the third part, the fourth part, and the fifth part. You would assume they'll take 24 minutes if they do it in parallel, and of course 4 minutes at the end. So in total, you're going to spend 28 minutes on this. Right. Now, Amdahl's law, if you remember, so there's a nice equation, but even without the equations and the formulae, you should be able to work this. Right. Now it says that if you have a process, the speed up, that's how much faster it's going to be. It's going to be where S is the serial part, and N is the number of processes that work on the parallel part. So this question is a little bit tricky, because some people, when doing this for Amdahl's law, would think, oh, I'm going to use 6 and 4, but it's not really 6 and 4. The question is, if there is one person doing serial, so that means you have to use 2 hours. So the wrong way to do this would be to say, oh, you know what, I have 4 minutes of serial and 6 minutes of non-serial. So this is a little bit tricky. Right. But the actual work that's being done to generate, so this means this is an output. The 6 minutes was supposed output at the end, but it's actually going to take 2 hours to do this. So in terms of proportions, this is 2 hours is 1 hour, 120 minutes. So it means 120 minutes and 4 minutes. So this is actually going to be the serial part is 4 over 124. Remember, it's a fraction. We have to use what fraction is serial, and this would be 120 over 124. This value and this value here, the two values, these ones, they add up to 1. So if it's 4 over 124, it will be 120 over 124 divided by the number of threads, 5. Right. Okay, so I'm just going to work this out. So 4 over 124 is 0.0322. This is 0.9677 over 5. Okay, so that's what we have. So this is 1 divided by 0.0322 plus 0.193. and speed up is 4.44, right? And so in the first case, remember it took the first, if it's serial, right? If it's just one processor doing everything, so for one processor to do the work, the amount of time that it took was 2 hours and 4 minutes. But if there are 5 processors, come on. We are saying speed up is going to be 4.44. So the amount of time that it will take speeding up, that means it will be 124 divided by, in terms of how much time it will take, 4.44, so that we can actually get the actual time it takes. So this amount of time it would take, factoring in speed up, uh, 27.92 minutes, right? And you see that this is actually similar to what we had before. It said 28. That's 24 and 4. So it's about the same. So there are 2 ways to work this out. You can figure out the speed up and then say, if it's serial, how long is it taking? And then use the speed up to determine the amount of time that speed up is determining. So if speed up is saying 4.44, then it means, of course, that it's going to be 124 divided by 4. Right. Now, this isn't difficult to understand. Just look at the first one that we talked about. Now, if there's one painter, if I'm using 2 painters, my speed up is 2. So how much faster am I going? I'm going 2 times faster. So that's my speed up. If I'm using 4 painters, my speed up is 4. That's why I divide 1 divided by 1 by 4, the amount of time divided by the speed up, the original. So this is the original time. Right. This is the original time. And then I am dividing by the speed up. Right. So this problem was a little challenging, and you had to think about what the numbers actually meant. You couldn't just stick it into the formula and get an answer. You had to sit down and think this through. Right. Now, what if there were, as the question said, 20 processors working on this? So remember, there was a 2 hours for the 6 minutes of 3D and 4 minutes of regular time remaining. Right. Now, if I'm going to have 10 processors, 20, the question said 20. If I'm going to have 20 processors working on 120 minutes of work, right, then we are going to expect that each of the 20 will get to work on 6 minutes of work, right? So if there are 6 minutes of work followed by 4 minutes, because this 6 minutes, remember there are 20 of them, so 6 times 20, but they are working in parallel. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 people working in parallel, this is 6 minutes off. But if you took all the time, it would add up to the 120 followed by 4 minutes. And so this we expect to take 10 minutes, right? So now that I have 10 minutes, and knowing that if it's one processor, it takes 124 minutes. My speed up for this, so this is the time it took, if they are 20, is 10 minutes. So my speed up is going to be 124 divided by 10, which is 12.4. Right. Now let's use Amdahl's law to work the same problem. Okay, so using Amdahl's law, so remember Amdahl's law was 1 over s plus right. In this case, our s, our shared part is still 120. Sorry, not 120, sorry. It's, sorry. Sorry, not shared. S is the serial. Right. So our serial part is right, and then our non-serial part, that's the parallel part. I think we did these computations before. We knew what this was and we knew what this was. Previously we said one of them was 0.0322. And the other one was 0.9677. And you'd see it's actually, once you've done the first one, doing the second, third, fourth, I don't know, 100th, it's easy to do, right? Plus 0.9677 divided by 20. Right? And this is 1 divided by, okay, and 0.9 divided by 20, 0.9677 divided by 20. And this is 0.0483. Right. And so our speed up is 1 divided by 0.0805, and this is 12.42. Right, so you see this is almost the same. The reason why we are getting it off a bit is I am truncating, I'm cutting off some of the accuracy, right? So if I have this speed up, I can then use this to determine how much time will it take if there were 20. So this is my speed up for 20 things, right? And so my time that I would take it for one thing divided by the speed up if there were 20 things would actually give me the time when there are 20 things. Right. So this is, remember, it was 124 minutes divided by 12.4, and the answer to that, 124 divided by 12. Is 9.983, which is almost 10. Right. So this is the time that it will take. Right. So I'm going to go a little bit further. Now, how much faster? So this is, well, it's a different question, but still based on this. So you can think of Amdahl's law in deep terms, or even if not Amdahl's law, knowing how to estimate speed up, right? So how much time is it going to take? I mean, what's the best performance possible? for this problem if I had multiple processors. Right. Now, if you think about it carefully, there is 120 minutes of parallel work, or work that you could make parallel, followed by 4 minutes of work that has to be done serial. Now, if you look at these 120 minutes, what if I had 120 processors? That means I'll take 1 minute. Right. What if I had 120 processors times 60? Right. That is, if I had 7,200 processors, that'll take me 1 second. And so I could keep adding more and more and more processors until finally the time spent here would be almost zero. Right? The time spent there will be